My name is Corey Scobie, and I'm the Vice President of Open Platform and Product Experience here at Akamai. So this essentially means that I'm one of the key advocates for you, actually, for the people in this audience today. Over the last few years, we've been endeavoring at Akamai to really open up the technology and the infrastructure of Akamai to the world at large. And that's one of the things that I'm driving in trying to get us closer to developers and architects and key influencers, operations personnel around the world, particularly when it comes to web performance, web security, etc. For those of you that are not familiar with Akamai, today we operate a globally distributed network. It's about 200,000 servers, a little more than 200,000 servers around the world in roughly 1,400 networks. What this translates to is we have something that we call the edge, which is basically the perimeter of our network. And it means that we have Akamai servers roughly within one network hop of about 90% of the world's internet users. So it gives you a little context of what we do here at Akamai. Our goal is pretty simple. We're trying to make the internet fast, reliable, and secure. And I think we can all agree, most of the people in this room probably have some pretty real knowledge about the fact that the internet in its natural state is not fast, reliable, or secure. So, that's a problem we've been trying to solve here as a company, and I think as a community at large for, the better part of 15 years. On an average day here at Akamai, we transit something around, our typical sort of steady state traffic rate is around 25 terabits per second. I think we have a real-time web monitor in the hallway there. I think you'll see it's registering about 60 million page views per minute right now, so that's the kind of volume that we see. And it translates to roughly somewhere, and it just depends on the day, somewhere between 15 and 30% of the world's internet traffic on a daily basis. So that's about all I'm going to say about Akamai. The next I'm going to introduce, I'm really privileged actually to introduce a colleague of mine, and tonight's speaker, Stephen Ludin. Stephen's been with Akamai and he's kind of girly about it, so he wouldn't let me say the actual number, but a really long time. For those of you that don't already know Steve, he's chief architect of our web performance products here at Akamai, and he's a pretty well-recognized member of the long-term performance community and the internet community at large. He's got an exciting talk on some of the latest developments that are focused on the challenges of performance, reliability, security, scalability of the internet. I think you're going to be really excited about that. So without further ado, Steve.
So I'm going to try to talk without the mic. Can everyone hear me fine enough? All right, great, because I was having a harder time with the mic than without. So thanks for coming. This is cool. I haven't been to one of these in a while, and it's good to have it here, and it's even better to find out that I'm actually talking at it. So I'm here to talk about kind of the newest and greatest, in some people's opinion, developments in web perf technology. Now, you're going to feel like it's a bait and switch, and I apologize for that, but trust me, stick with me. In order to really understand what we're talking about when we talk about H2 or QUIC or UDP or H3, everyone needs to get a baseline on why they're important and what problems they're trying to solve. I go around, I do a lot of speaking, and I find out that kind of like we've forgotten our multiplication tables when it comes to how the internet works. So I guarantee there are some in this room who know 10 times more about this than I do. I'll buy you beers afterwards if you just, and at the end we'll have plenty of time for questions. So thank you, Corey, for the intro. I'm Stephen Ludin. I've been at Akamai for 13 years, which is testament to what a great place this is to work. Working on some of the biggest problems out there, some of the coolest internet trends, and working on kind of the cutting edge technology, being involved with H2, with QUIC. It's good stuff. I'm on the board of Let's Encrypt, which is something I'm very proud of. You guys all know what Let's Encrypt is, right? Yay, all right. And a couple other things, and it's my privilege to be here and speak to you guys tonight. So, to talk about the future, we have to talk about the past. And we're not going to go quite this far back, but we need to go back to about 1972 or so. and with the humble IP packet. So this thing is why we all have jobs, right? We're all here because of this little bit of electronic data. Now I tried to find an image of it, and if someone has access to an oscilloscope and can actually plug in the Ethernet cable and get a 15K Ethernet packet with all the little jagged things, I'd love to see it. But this is what I have for today. Now, this thing is really, 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 really simple. You've got the source IP. I'm sorry, I keep looking over my shoulder at my slides because I don't quite have them memorized. You have a source IP, a destination IP. Where is it coming from? Where is it going to? A checksum, time to live, 15 bytes max, and data. That's all it is. This is the magical thing that our world is built around. And the theory is you have the internet, you have a packet, and it shoots across the world like that, and boom, you've got communication. In an idealized world, the Google map for a packet would look like this, about 15 milliseconds from LA to New York, which I believe is the rough speed of light in a copper cable. Physicists, again, beers later. In reality, the internet is not one big thing. It's a network of networks that grudgingly agree to work with each other. I can go into all the reasons and the sort of the upside down financial model about the thing, but the path that these things take is very circuitous, and on the back just as bad, and it goes back and forth. This is where you get things that are more like this. You know, a cross-country trip that has many bottlenecks and problems, and you end up with traffic, and when you want is a coordinated flight of packets from one place to the other. So that's what we're here to solve. So there are two rules for internet performance, and we have very little control over it, but bear with me. A, round trips are bad, all right? Everything we've been doing in WebPerf for the past 7 years or so has really been focused on trying to reduce round trips. How do we make things smaller? How do we open up window sizes? How do we go ahead and make everything so that we don't have to go back and forth quite as much as we might have to? Second rule, if you need a round trip, make it fast. So this is, one of the Souders rules, as I call them. Get a CDN, terminate close, so you're not going across country, so you're just going locally. And my only Akamai plug, use Ion. Trust me, literally the only one. So what we're going to talk about today is TCP, H1, and TLS1.2, and kind of how they morph into the technologies that are actually much more interesting. Hopefully when you leave here, you will have a really solid understanding about why people are talking about these things over here and why they're interesting. By the way, I should note, disclaimer, there is no such thing as HTTP3. It doesn't exist yet. There's no working group, but we all know it's coming. But just keep your imaginations open. All right, TCP, our friend. So to understand TCP, you have to understand what it is. An IP packet has no state. So what the TCP stack does is it creates a state with the three-way handshake. SYN, SYNAC, ACK, hands up, everyone who's very familiar with this. Okay. All your hands down. There's this thing called a SYN, a SYNAC, and an ACK. It has to go back and forth 3 times. I like to call it the yo, sup, and sup. All right? It's the way two different things create this virtual circuit, all right? Now the problem with this is it has to go back and forth. 100 milliseconds is not an unreasonable amount of time for this whole thing to happen, all right? So, second bit about TCP is congestion control. So ideally, you would think you just want to take all the packets and throw them on the wire and hope they get there. But of course, things don't work that way. The internet would collapse, it'd be bad, you wouldn't get anything done. You have this. So this is a classic graph of showing the throughput on a TCP socket. So what happens, you start off in this area called slow start. Slow start is where it politely goes, I'm going to send 1 packet, I'm going to send 2, and no, we don't start at 1, we start at 3, moving to 10 now. But you get up to a point where you get to a threshold and you start to add 1 on. So it's very, very polite. And the reason why it does this is it really has no concept of what it's trying to talk to. This was developed when a 300 baud modem was bitchin' fast. I mean, this was a different world. So the idea is it comes up and gets to a point where it tries to figure out. And then it has this thing called congestion avoidance, where I'm going to go ahead and send packets. Now, we don't want congestion avoidance, we just want to send data. But what happens is it gets to a point and something happens. It goes, oh my God, this packet came out of order. Oh, I didn't see this packet, and it freaks out. The default TCP stack will go ahead and just cut its window size in half, which means significantly less data is going to get through in each round trip, up to the point where it has to go ahead and do slow start all over again. When you're staring at your device or at whatever, and you're going, what is happening? It's usually something like this. Now, what we want is this. We don't want this jagged up and down thing. We want to try to get to a point where we have flat performance. It's not as high as the peaks that the other congestion control algorithm showed, but you're going to get more out there. And so someone says, well, UDP can kick TCP's ass, so we should all need to move the UDP. And now here's our first myth busting of the night. So what is UDP? So here's a TCP packet, and here's a UDP packet. You can see by the picture they look exactly like each other. But in reality, what TCP is, it's an IP packet with congestion control. I mean, I'm glossing over some of the details. A UDP is an IP packet on its own. It's a datagram. You can send it, you give it out, there's no acknowledgement if it gets there. But now, if you want UDP to be reliable, if you want to go ahead and have a stream of data and know that your other side got it, you need to add a congestion control. So essentially, by a transitive property, UDP and TCP come out to be the same thing when you get into an application space. Now, what is the difference and why do we care? This is really where it comes down. UDP, or TCP, is traditionally, for the past 35 years, put in the kernel. Things in the kernel are hard to change. A kernel upgrade is an OS upgrade. You know, how many of us says, you know, the Mac is bugging you, you want to upgrade later, tomorrow, and they get it harder and harder to ignore that thing. But these things are hard. Not to mention, the people who can change this are, you can list them on probably one hand. You've got Microsoft, you've got Apple, you've got the Linux world, which is, I don't have enough fingers. But, you know, it's hard to make those changes. The real thing about why UDP is exciting to people is that whatever you create, whatever stack of communication you create is in user space. You can go home, open up Emacs or VI, and do your own thing in UDP and create a stack that's fast. So when people talk about UDP as a great transport mechanism that's better than TCP, what they really mean is that they can create a more flexible, smarter congestion control algorithm in user space, maybe that's more resilient than what you can get with TCP. Now, yes, everything you do up here could be ported down there. It takes time, but that's why UDP is exciting. So the bad about TCP, you got the three-way handshake. It takes time. Congestion control is a little jittery and nervous, and what was the word you used, Corey used to describe me? Was it, I can't remember, girly? And it's very hard to change. All right. Which brings us to HTTP 1. Now, HTTP 1. This thing is the other reason why we all have jobs. You know, all of us are employed because they decided that they wanted to go ahead and do H1. But since H1 came along, the web has changed just a little bit. It's not the same as it was before. Welcome Yahoo. Anyone remember this? Anyone literally, I remember going to this page trying to find data. And it was awesome until a search engine came along. And this is how we access the web. This is what it looked like. We used things that looked like this. 28.8K modems, very fast. But then the world changed and we got things like DSL and computers that looked ripping fast. And now, what's the most amusing thing to me is we're now moving to a world where these are our lines, and we want to go ahead and use little phones like this to communicate. We're going backwards. It's cool, it's fun, but it creates a whole bunch of problems for us in this room. H1 was not developed to deal with all this stuff. H1 was not developed for 4K cookies and headers that are bigger than the content. So we need to change. A modern web page. I've been doing these types of talks for a while, and I haven't looked at HTTP archives for a while. I was shocked when I pulled these fresh numbers out yesterday. Almost 2 megs for your average web page. This is the top 1,000 sites from the HTTP archives. So not the whole corpus, just quote unquote the important ones. 125 objects, 28 domains, separate domains. That's at least 28 of those fun little handshakes you have to do, all right? I mean, it blows me away what a modern web page has now. And what happens is H1 makes a connection, and it makes a reply. It makes a connection and a reply, and back and forth. There's no multiplexing. It can only do one thing at a time. But you say, but wait, my waterfall shows a whole bunch of things happening at the same time. And so what it does is it opens many connections and many replies at the same time. All these things suffer from a couple of problems. First off, having lots of connections on your machine is going to go ahead and have a very inefficient use of resources, whether it be for just memory usage or whatever. Also, you're getting around all of those fun congestion control algorithms. You're opening up tons of sockets. It's just bad juju. It's what we had. It worked well. We sharded. We all sharded, right? Sharding was good. Stretch it across more, so we got more sockets. All right, so we want to reduce round trips. We want to make it simpler for devices, and we want to avoid this and get this. So the bad of H1, header line blocking. Headers are incredibly verbose, and TCP is not very efficiently used. All right, and now it brings us to TLS. So my prediction, this is a little bit of a tangent, is that in the next 3 to 5 years, the DV certificate will be the new clear text. So people like Let's Encrypt are going to help all of us have certs. It's going to be easy to use, easy to install, cheap, very wonderful things. You're going to see things like this will be normal for your EV world. This is what you're going to start seeing at some point for your for just plain old HTTP. It's going to be scary. It's going to be, this is not a secure connection. Do you really want to do this? It's going to take a little while, but we're going to get there. TLS is here, and it should be everyone's kind of de facto starting point these days. But it has problems. It has a big handshake back and forth. Hello, hello, finish, finish. What cert do you want to use? What do you want to do? It's very chatty. So now you have even more round trips. Go ahead and add the TCP handshake on the front of that, and it could be a couple hundred milliseconds before you even get started to communicate. With HTTP and many, many handshakes and many, many connections, this problem is exacerbated. It gets much worse. So we want to require TLS. All of us want to make it sort of the thing that we need to do, but we want to preserve performance. So here we are. TCP isn't optimized. HTTP works great on GeoCities. Is GeoCities still around? And TLS is painful, all right? Or it doesn't have to be painful, but it is. So, to the rescue. H2. H2 was a really fun project. There was, anyone here involved in the working group? All right, I'll put my hand up. It was a very fun working group to be with, a lot of opinionated and smart people in the room, meeting at different places around the world, but it got us very, very far. Now, in the beginning, no one thought there was going to be another HTTP. In fact, members of the core working group, IETF, are on record as saying, H1 is here. There will never be the appetite to go ahead and upgrade until someone came along and created Speedy. And what Google did was showed more than anything else, more than just the fact that you can improve on H1, because everyone knew you could improve on it. You know, everyone had their own little, backroom operation about what was better, but that the web was ready to upgrade. So Google created it, Google put it on their servers, and then the most significant thing that happened was Firefox implemented it. And then at that point, it was gangbusters. This thing is real, and the working group got started. So the whole point of the working group and the whole goal of H1, this is from the charter from IETF, was to go ahead and address the head-of-line blocking problem, increase parallelism, and then a bunch of things. But one of the fun things here is we talk about perceived latency. We don't actually have to make the page faster if the page feels faster. And I think all of us have been living that sort of perceived world for a while. If your customers feel like this is a faster experience, it doesn't matter if it is or not, hence why it's in the charter. So H2 brings us multiplexing. I can do more than one thing at the same time. Header compression. Now, you can quite literally, in a somewhat pathological case, have a 0-byte header. Try to figure it out. Prioritization. Anytime you have multiplexing and can send everything out at the same time, you need something to say, this is more important than that. Otherwise, what will happen, and you can probably figure out a way to tweak your browser to do these experiments, you'll get all your bytes down faster, but you will stare at a blank white page for about 3 seconds because the right stuff isn't coming down. Prioritization is very important, and then there's push. The fun thing about push is every single part of H2 that went through the working group was just given an examination. Nothing could go into the spec until there was a working example of this in the wild, except for push. No one figured out quite what push was going to be or how we were going to use it, but everyone knew it was going to be a great thing. So right here, push, huge world, this opportunity for one of you to go out and make the killer app using push. So go out and do it. But you'll notice that there's actually no requirement for H2 to use TLS. It's mentioned as a suggestion. And there's nothing in it about using a single socket, except it's a goal. So everything we hear about H2 about needing TLS or using a single socket is actually an implementation detail. What has happened is the browser vendors have basically said, TLS is important. We are going to make certain that this traffic stays safe, and we're going to use H2 as an opportunity to push TLS. Big believer in it. I think it's a great move. But the other thing is the single socket. This is going to be another thing to keep your eye on over the next couple of years as H2 evolves and gets a lot more traction, and we start to really push, web page test at it and pick it apart. Will the single socket survive? Or will we start to see browsers using multiple sockets? It's going to be interesting. So H2, rather than going one at a time, all the requests go out at the same time, all the responses come back. They do not have to come back in the same order. This is very important. If, for example, there's a packet dropped, or a frame is bigger, or whatever, one element can come back out of order of the others. And of course, you get the big orange box of saved time. This is real, it happens. And the nice thing about it is, as implemented, it's multiplexed over one socket over TLS. There's H2 for you. But remember this problem that we have with TCP, H2 is top of TCP, or top of TLS, which is on top of TCP. We have this. And this is what I like to call the eggs in one basket problem. All right? You have now taken your, what did we say, was it 28 connections some very large number of connections, which are all working in parallel, which could all have their own individual TCP problems, and putting them into one TCP socket. Anything happens in that socket, and you got a whole different kind of header-line blocking. All right? Sorry?
52 TCP connections.
I said 52. Great, thank you. Someone's keeping track. All right, so we need better congestion control. That's what it means. Doesn't mean H2 is broken. It means we need better congestion control to really get the huge full benefit. So how can we efficiently tweak the congestion control algorithm? I touched on it a little bit earlier. Now, let's say you're Google, and let's say you control a huge browser base and a huge endpoint. What can you do? Pretty much whatever you want to do, right? And so this is how we got Speedy, and this is how we got something else. So how do we use UDP to create a quick internet connection? And from this came QUIC. All right. Now, I poke fun at Google, but note that I say that with huge respect. What they've done is a great thing. So QUIC. QUIC is, I had it up there, and now I can't put it together. QUIC UDP internet connection. All right. So what is QUIC? So going back to our basics, what are our parts that we're pulling together? So what they did is they took TCP, they took Speedy, and they took TLS, and they said, we're going to take all of this and implement it over UDP. All right? So in essence, in some ways, if you squint at Speedy and says it's kind of H2, and well, TLS is there, and well, we have to re-implement TCP, essentially, you could say it's H2 over UDP. That's really, really rough. They also wanted to add forward error correction. Forward error correction is the idea of, I'm going to send a little bit of extra information in each packet. You know, it's unnecessary. But if you lose a packet, if one doesn't get there, because remember, UDP is unreliable, something could drop, you may have enough information to not need that lost packet. So in concept, this is a great thing. Obviously, if you are in a situation where you're sending twice as much data, that's bad. So the scientists out there are trying to figure out what's that optimal amount where you just send a little bit more to be able to deal with that drop packet scenario. Huge, huge potential benefit. User space congestion control. This is what I was talking about user space versus kernel space. QUIC is implemented inside the user space. It's easy to upgrade. It's easy to change. Browsers can upgrade, and you have QUIC upgraded. Yay. And it has loss resilience. So this comes from your forward error correction. So now, done some tests of this at Akamai, and this is what QUIC looks like with 0 loss. And it was a simulated 3 megabit link, whatever, or something like that. This is what TCP looks like. You go ahead and lay them over, and they actually look about the same. You know, I could poke holes at the little orange dips there, but any of you who have run these enough know that there's enough variability out there that this isn't significant. And this makes sense. TCP, when it's working, when there isn't loss, when the windows have opened up, when it's doing its job, is going to be optimal. QUIC is just being optimal in more situations. So, enter loss. So now we introduce 1% loss into the equation. And now we get a whole different story. QUIC doesn't look quite as good. You know, it's correcting, it's trying to adjust. But TCP fares much worse. All right? And now, when you bring loss into the equation, this is where TCP and QUIC, and UDP, sorry, TCP and QUIC, is that right? Yeah. Start to diverge, and you start to see the benefits. So the next question is, okay, let's talk about QUIC versus H2. Now, this study was not done by us. It was presented at the working group meeting, or actually the HTTP workshop meeting, I believe it was in Bremen over the summer. And this is taking a look at QUIC versus H2 and in realistic scenarios, okay? And it looked at things on different capacity links. It looked at different sizes of pages. Small, medium, large. I don't have what was small, medium, large on the tip of my tongue, but I can look it up. And what you see here is that in general, and this is the what percentage of the time is it doing better than H1? So this graph is a little bit upside down. So you can see on the lower side, smaller pages, QUIC tends to provide a bigger improvement than TCP does. This has a lot to do with slow start. So TCP takes a little bit longer to get going. QUIC starts right out of the gate going really hard, all right? But as you get up to larger pages, that difference starts to go ahead and diminish. And once again, that makes sense. TCP gets up to a happy, steady state. It's going to be close to optimal, and you're going to start to see it. But now, what you don't see here is if this was very lossy, I would expect there to be QUIC would be significantly better than H2 in this case. I think I said TCP when I meant H2 in there. You just translate. All right, so now QUIC also has an idea of a zero RTT connection establishment. All right, there's the ability to go ahead and basically do the TCP handshake and the TLS handshake in one packet. And this is, of course, they've seen you before, they know who you are. This is a good thing. So now you send your data in one packet. So think about any request that you have that your browser is creating to your web property that is under 1,500 bytes. It could literally be one round trip and the data is back. This is phenomenal, right? So that's interesting. And TLS 1.3. So the goals of TLS 1.3 were to basically clean up 1.2. Anyone who has been paying any attention to the news for the past couple of years probably can't get away from the fact that it seems like there's another incident, some new problem with OpenSSL or TLS or whatever. There's a lot of cruft left in TLS 1.2. There are ciphers that are in it that are no longer there. We should not use that anymore. So they want to clean up the cruft. They want to improve privacy. They want to figure out a way to make it even better when it comes to actually the crypto and authentication part that TLS 1.2 has. Improve latency, which is what we care about, and have a continuity. So we're going to talk about latency because that's our big thing. So removing cruft, any of you who care, static RSA, gone, all right? So that I have an RSA key and you're gonna go with pre-master secret and come back. That whole bit is gone. It's now all gonna be ephemeral keying. Renegotiation, gone. Non-AEID ciphers, gone. So all of this stuff is a goal to get rid of stuff that is no longer used, deprecated, yet is still part of the standard. They also are working on trying to get to that goal that QUIC has of a zero round trip connection establishment. One of the first goals is if I've never seen you before, I don't know who you are, I want to get the round trips of the TLS handshake down from 2 or 3 down to 1 round trip. And this is where they're going with that. And if I have seen you before, if I know the endpoint, I want to be able to send the client hello and let's get going with my data right away. This is using a simplified session resumption type of thing so that. Now, many of us have our customers come to us and they have connected to us before. They've done the handshake, they know who we are. So seeing this type of performance improvement of having a zero round trip TLS establishment is real. And it's gonna be very exciting when we get it. Which leads us to HTTP 3. The big asterisk there is to indicate that there is no such thing, but stay with me. So many people look at H2 and say, well, H2 is a speedy. And immediately say, well, is H3 to QUIC? And the answer is we don't know yet. It's possible. A lot of it depends on what happens with QUIC over the next couple of years. Months, years, what am I talking about? So we'll see. But what we are going to see, and this is my prediction, is you are going to see a TCP, something, improvements on H2, things that we've learned, things we want to get better, plus TLS 1.3 over UDP. So if, it wasn't that bad, was it? Help? Someone? Lights? Well, I'll keep talking as long as you guys don't get scared. So if this feels like the QUIC slide, it should feel like the QUIC slide because this is really how we describe QUIC, except slightly different things on the left-hand side. So just like Speedy and H2 aren't the same thing, we're going to learn a lot from, it's getting darker, we're going to learn a lot from our experiences with H2 and QUIC, and I guarantee you it's going to feel a lot the same, whatever it is we come away with it. So where are we? When can we start using all this fun stuff? So H2, the great news is it's here. It exists. I think this says, you can't read it, maybe I can read it. Oh, according to Can I Use It, 71% of existing user agents in the wild have H2 already. I mean, that blows, it's phenomenal how quickly this happened. Google supports it. We've been using H2 in our quietly in the background for quite a long time now. Akamai supports it. So this is, we're all using it. Who here has a plan for H2? You on your web server or whatever? Come on. Who here wants a plan for H2? Yeah, okay, thank you. Gosh. Anyway, oh, this is, now I'm backlit. Actually, if you can put the lights on really fast, open up, I can like move like this. So QUIC. QUIC isn't, understandably, it isn't quite there yet. Chrome supports it, so anyone who's been using Google Docs, doing searches on Google, anyone here do searches on Google? All right, now we see hands. Has been using QUIC, as long as you're using Chrome. And Akamai, we're working on it. We have a plan. We'll have some sort of support for this coming out in the next year. Stay tuned. And TLS 1.3. All right, so anyone who wants to really join a very fun working group, join the TLS 1.3 working group. These discussions are lively, we'll say. I thought people are passionate about H2. People are more passionate about crypto. The goal is to have the draft done this year. I don't have an exact date on it, and I was told that OpenSSL is going to have it by early 2017, maybe late winter, we'll see. But so this will be a great thing. Now that puts in perspective about some of the things I'm talking about are not tomorrow changes, they're next year, which internet time is like 10 years away. So, but stay tuned. And H3, this is the big question mark. Any of you who weren't involved in the H2 process and said, gosh, I'm really bummed I missed that whole thing. I mean, I love talking about byte order. You'll get to do it again, all right? It'll happen, stay tuned, subscribe to the IETF mailing list, and you too will get a chance to change the future by working with H3. So, the whole idea of these new protocols is they are really built upon trying to fix problems that we put in place 40 years ago. They're working with an aging, somewhat upgrading ecosystem. They're trying to deal with new use cases. So by understanding the real nuts and bolts about where all these things came from, I really hope that you leave here with a better understanding about what is QUIC, why is TLS 1.3 important, what is H2, what problems was it trying to solve, what problems has it not solved, all right? So then when you go and back and you want to have a discussion with your teams about performance and should we do this, should we not do this, you can actually really start to understand those waterfall charts, those TCP dumps, and get a good feel for why and when one of these technologies might help. They will not help in every case. There's no such thing as the perfect pill to solve every problem out there. The goal is to get them to help in the most of the cases. You know, get that 75th, 80th percentile better. improve everything, make us all better performance, right? Performance is good. And with that, I'm going to leave it up to questions.